Today we're going to be looking at 5th Gen AMD 9575F for CAE. If you have any questions during this webinar, just put them in the chat. They'll be emailed us at the end and we'll answer those offline to you after the webinar. The agenda for today is we're going to talk a little bit about who TotalCAE is if you're not familiar with us. We're going to look at the new 5th Gen AMD 9575F, go over the benchmark systems we used, talk about some converged CFD results, a real-world customer analysis example of trying to take a 56-hour rundown on using the new AMD, go over some crash, implicit, other CFD explicit results, things to consider when choosing a CPU, some application considerations you want to be aware of when using AMD, a little bit about Intel MPI versus Open MPI for AMD, layout optimizations, just that has a novel architecture, some things to know how to make sure that you're using it to its peak efficiency, a little bit about AMD on cloud, and then how to get some more information. So if you're not familiar with TotalCAE, what we do is basically help us customers reduce their simulation time by up to 80% using high-performance computing. That either is with an on-prem cluster that we either sell, manage, or manage, or the cloud. We manage all the IT from everything from when you submit the button till you get your job results back. TotalCAE takes care of all the upkeep of your apps, the cluster, the cloud, the MPI layer. Basically everything that you need to do so that you could just focus on engineering and not IT. So we support hundreds of different applications, and we just have 3 clicks. We have a portal that you could just upload your CE models. There's also a CLI, an API, many different ways to integrate with TotalCAE. So if you want to just be able to focus on engineering, just want to throw your model in a cluster or cloud system and just have the results show back up on your desktop, that's basically what we do. And we include our software that makes that really easy to use and our managed service, and all that combines together to really make the HPC as simple to use as possible, a reliable tool for your engineering department. So today what we're here to talk about is 5th Gen AMD. So this just came out. We just received our first one a little bit over a month ago. And what the new 5th Gen has is faster DDR 6400 megahertz memory. That's great for CFD applications that need more memory bandwidth. The AMD designed is a bunch of little what are called complexes that are kind of glued together with I/O to make these giant core machines that you can see the AMD does. And so this one has 8 core Zen CCX complexes, and those complexes are like little chiplets. Each one of those chiplets has 32 megabytes of L3 cache, so the whole chip has 256 megabytes of L3. And then you can have up to 64 of these cores in a CPU package, like a chip that you might see physically look at. It does have now full AVX 512, though realize if you'd have an Intel compiled AVX 512 binary, it may not just work out of the box on AMD, but it does have AVX 512 now. And as codes get compiled for it, you'll see the benefits of AVX 512. There's many C applications that are compiled for AVX 512 support. It's like a special way to speed up mathematical operations. So this chip really is great for CFD and the things that need high memory bandwidth. It also has on this particular chip, a 5 gigahertz clock rate, which is very high. So if you have even kind of lower core count jobs that can boost up to the 5 gigahertz max turbo on these, you're going to see some benefits, which we'll show later. So there is many AMD 5th Gen AMD SKUs. This one is kind of, I pointed out here, the 957F. F means high frequency. It's a pretty good processor for a wide variety of CAE and CFD codes. Got a lot of cache. So this is the one that we chose to benchmark today. So the benchmark system that we have is 64 cores. The base frequency is 3.35 gigahertz, 64 cores in this particular box, and 2 terabytes of memory. We also have a 5th Gen Intel system. We've done a previous webinar on 5th Gen Intel. Similar, 2.3, can't get that 5 gigahertz. Intel's kind of at 4 gigahertz on 5th Gen, 96 cores. Though to make it equal, we're using 64 cores on many of the comparisons, and then 256 gigs memory per core. This particular chip has a large L3 cache as well, 300 megabytes. So I'm going to start off with Converge, these are all public information. Some of the ones I can't mention the exact application, but this one is all public. So the CFD Converge run here ran on 3rd Gen AMD, 128 cores, 3 hours and 54 minutes. 5th Gen AMD on half the cores ran in the same time. So that's just an amazing improvement on a per-core basis, generation over generation from AMD. And of course, the 5th Gen Intel on 64 cores runs in a similar time frame. But definitely per-core performance on 5th Gen, especially if you're on an older AMD or Intel, is going to be a huge boost. And so a real-world example, sometimes the benchmarks always look good, but we had a client come to us and said, hey, I have this run. It's taken 53 hours, and they paid $16,000 years ago for this compute box. And so they're like, I need to get this runtime down. What can I do? And they're running on 56 cores of this 3rd Gen Intel. So we were able to get that down from 53 hours to 17 hours. And not only on 5th Gen AMD, which looked very, very good. Similarly, 4th Gen Genoa X is also a fantastic box for CFD. It had 192 cores to throw at it. And, here's the pricing kind of on the right. So it was hands down the bested the Intel, price performance all around. Really great for CFD. So if you want that L3 cache, I pointed out just because CFD needs good memory bandwidth. And while the memory has gotten quite expensive on these new chips that have this high bandwidth, the higher L3 caches kind of help with that too. And you can see on the 2 terabyte node, that machine on list price with 64 cores is quite expensive. Is quite expensive compared to one with lesser memory and double the cores. So just be aware, memory has gotten more expensive, and you want to right size the memory to how much you might need. Now some just other results just to show some of the generational improvements. Again, another case of crash. A job here taking 64 cores on 3rd Gen, almost 4 hours. 2 hours, 30 minutes on 5th Gen AMD. Again, just great per core performance improvement. And then 5th Gen Intel, staying in there too. Here's an example where that 5 gigahertz clock rate is very nice. So on implicit codes, they don't often scale to a lot of cores. So even though a machine might have 64 cores, if you don't use them all, the remaining cores really speed up in frequency, and that allows you to then run up at that possible 5 gigahertz. And so in this case, just running this 24-core job out of the 64 on the AMD and the 96 on the Intel, you can see that it it has a very nice runtime, an hour and 15 minutes compared to an hour and 40 on the same core count. If you're licensed by core, having that 5 gigahertz processor is quite nice. Similarly, this is a per-core licensed CFD application, just to show, that sometimes, it can go back and forth. Memory bandwidth is kind of key in a lot of these, and just in this case, it was just slightly slower, but pretty much the same as the 5th Gen Intel. An explicit code here, similar story. That while the Intel is slightly better when you undercore it because you have more L3 cache per core, still both are fantastic results compared to previous generations. So what do you want? Some things to consider when choosing a CPU. One is, how's your application licensed? Because if it's licensed by core, then that per core performance becomes more important. If you have a many CFD applications now have unlimited core licensing, and for those, just it isn't as important because you will probably want to run 192 cores, possibly before 64 cores, just depending. But you're not core bound, so that definitely can make a choice of which CPU you want to use. How many cores per job do you run? If you run like 1-core jobs all the time, maybe you don't really need to pay the premium for a 64-core high memory bandwidth solution. Do you need my high memory bandwidth? Occasionally, older generation might be cheaper just because you're paying a price premium for super high memory bandwidth, large L3 caches that not all apps take advantage, but CFD definitely is memory bandwidth bound. And does your application require Intel MPI, heavy use of Intel math kernel libraries and Intel compilers? Sometimes those can still run on AMD, but you may be you may run into odd issues. Normally, many of the vendors now are compiling AMD optimized binaries and giving you other options, other MPIs, as Intel MPI is not officially supported on AMD, though it is known to work at 2110 and later. The other thing is AMD is definitely more power efficient. So if you're like strapped on power, sometimes you can squeeze a little bit more overall throughput in the same power envelope if you happen to be power constrained. So I mentioned that Intel MPI is not supported on AMD officially, but OpenMPI is a fantastic MPI. Many CFD solvers do default to OpenMPI. And, so as long as your application gives it an option, this particular CFD app has both options. I just wanted to show it gives the same runtime. On shared memory, you're almost going to see no difference. Sometimes on large scale out jobs, depending on your interconnect, and especially on cloud, different MPIs do have a performance impact. But just be aware that you may have to dig under the hood of your application a little more. MPI is a thing called message passing interface. It's kind of how parts of between the processors and nodes data is interchanged. So you normally may not care about what MPI is there, but when you're running on AMD, you may need to be a little bit more aware and how to configure it. So, just a kind of a list of if you're using the latest applications, again, they almost always will have modern enough versions to run. It's only some clients want to run really old software that has very old versions of this middleware, and you really want to try to be on later versions to take advantage of the later AMD. So you can see here on this table just some popular apps. All of them have the minimum Intel MPI required to function, which is great. And they all have another option, another MPI, either OpenMPI, MPISH. There's many of these MPI flavors, platform MPI. All of these are available, so you got a pretty good flexibility. But when you do install the apps and are configuring their high-performance computing cluster, you do have to adjust them to make sure you're taking advantage of the hardware, and that's something that TotalCAE takes care of in our system, so you don't have to really worry about it. So we already showed that. I want to talk a little bit about tuning for AMD chiplet design. So I mentioned before that when your app, the chips are actually like 8 little Z5s or Zen 5 cores, and each one of those complexes has 8 of them and shares a cache. And in this particular diagram here, there's 16 of those little 8-core chiplets. So that means we have 128 total cores in this box. Now, the reason it matters is that when you're running a job, each one of these green boxes is kind of a little chip. Maybe let's say we want to run a 16-core job. Well, the optimal way to run 16 cores out of the 128 here is to have one core run on each of those little 8-core chiplets. And the reason for that is you get maximum memory bandwidth. That one Z5 core gets the entire 32 megabytes of L3 cache, which is kind of like a buffer into memory. And so this is the optimal layout. And where people sometimes run into trouble is, when they're trying to get performance on AMD is maybe it's not putting it in the right place or non-optimal, or you pick a odd core count that doesn't lay out really nicely to the CCX complexes. And and if you're not sure what it's doing when you're running your app, like on Linux, you can use the top command, and you're going to be able to see, like in this example, there's the first 8 cores. One of the cores is 100% utilized, and the others are idle. And the next one, the same. The next 8th core is 100% utilized. The rest are idle. And that means this is laid out exactly like I showed in the previous diagram. So each one of those cores is very busy doing work, and the others are idle, giving the one remaining core full maximum memory bandwidth. Now, if you use all the cores, there's nothing to really do. But sometimes, that might not be the highest performance. It just kind of depends. But yes, and you'll see in many different designs that sometimes people under core systems to get better per core performance for memory bandwidth on CFD apps. But I just wanted to kind of show that because it does trip people up quite a bit. And if you use new versions of apps and the latest versions of Red Hat, this most of the time it does the right thing. So now, if you're wanting to run on the cloud, as of today, there isn't any like 5th gen AMD that has high-speed interconnect connected, but there are great 4th gen options. HBV4, HBV5 on Azure, fantastic 4th gen AMD options will run very good. AWS has HPC CAE, also 4th gen Genoa. So these things, so you can totally run AMD in the cloud. I'm sure 5th gen will be out soon, and hopefully the 9575F. Often the clouds have the high frequency processors available, but high core count they definitely will. So just keep an eye out, and I'm sure. But if you want to run today, don't worry, you'll get great performance out of the HBV4 and V5 from Azure. Finally, if you're kind of interested in a specific application recommendation, we do have what we call blueprint guides for different apps, where we go through the best cloud systems, on-prem systems, chips on the particular one that you're interested in. So if you're interested in a specific app, reach out to info@TotalCAE. We can provide that to you. And I just want to say thanks for joining today's webinar, and hope to see you again on the next one.